Okay, so run the methane dash oxidation example. So mouse over here. Or, oh, take a look. Okay, good. Okay, so this looks a lot like the other RMG jobs until we start to get these updating. We start updating unimolecular reaction networks, and so PDF tends to give you a lot of. We tended to err on having a lot more warnings than perhaps is really necessary. So because despite the fact that we have all these warnings up here, this is all normal. But so as you can see here, what we're doing is we're looking at this network is constructed, and it's telling us what the isomers are. So in this case, it's just ethane. It could be two species reacting together. It could be not isomers. But we're starting the network from ethane, and it's listing the possible product channels. It can split on the carbon-carbon bond to make two methyl radicals. It can split an H atom to get a methyl radical and a hydrogen radical, and it can split off into methane and CH2. And as we go through, you'll see other ones of these. You also see a lot of these warnings, which are essentially each iteration is comparing what it expects to get with what it's in estimation, what it's actually getting, until it gets in reasonable agreement.
And so that's the discretization of the energy continuum that Bill was talking about. So initially, the estimate is very far from the expected value, so then it increases the fineness of the energy discretization and to improve the estimate. And then eventually it gets close enough and it stops.
And so you can see in this network has a reactant channel. So what it's looking at is what happens when O2 and a methyl radical essentially combine to make this isomer, which has a number of product channels. Some of these are unimolecular product channels, and some of these are bimolecular. And as you can see, like here, what this also results in is you get a lot of these reactions where this is the input channel, and these are all of those possible output channels. Some of these are like well-skipping reactions that will skip over wells that wouldn't normally be an RMG reaction, but are because of the pressure dependence. And is there any other interesting part of this? I'm going to take a look at the chemical file, but do you think we should look at that?
There are other options in reset the job that they usually exist.
In the PDAC?
Yeah, that would be good.
You mean should we try other options?
And just explain the option.
Explain it. So method. So method is your choice of method is built in through modified strength collision, reservoir state, and CSE. The maximum grain size is the largest the largest section of the energy.
Yeah, for the energy grain.
Yeah, for the energy grain, the largest energy grain is allowed to have.
So the course is
the course is grain.
Yeah.
And then the minimum number of grains will be the number of those in a given, per given species, the number of energy states, the minimum number of states it requires, which will increase if it can't handle it. And then the temperatures and the pressures are the...
These are the range for the Chevy Chevs, right?
Yeah,
Just like,
well, but this is the range for the Chevy Chevs. I think these are the points it takes it at before it fits the Chevy Chev.
yeah. So the KFTP is a very funky looking function, and people have tried multiple functional forms to try to fit it, and without great success. And so current method, it's in Chemkin and Cantera, and RMG prints it out, is basically just fit it to a Chevy Chev polynomial in logarithm of pressure and probably 1 over T. I'm not sure. Some T scale. And so the master equations are solved for different pressures and different temperatures, a whole bunch of them, set by that number in the input. And then, here we go, yeah. And then these are coefficients.
What?
Mm-hmm.
What do you,
Go back
Can you make it bigger?
I'm not sure in Nano. How do you do that in Nano?
Like, well, you have to modify your terminal.
Okay.
Bigger font size.
Oh, it's just,
Yeah.
Yeah, that was control shift.
yeah.
All right.
There you go.
Yeah, that's good. Okay, so Chevy Chev polynomials are it's a fitting form that's like a sequence of orthogonal polynomials and what's the coefficients of them. And this is the range of temperature points that were used, the range of pressure points that were used, and then probably how many polynomial coefficients, how many polynomials in each dimension, the t dimension, the p dimension, were used. And these are all their coefficients, so probably 6 times 4, probably 24 things here. You can control this. You probably won't know what to do, so you might want to just take the defaults that Matt suggested. But occasionally, you might know what the real K of T and P were at some points, or you compute them. Actually, in the result, it shows the fitting error, right? I think it's
in the PDEF network.
Yeah,
okay.
I think
I can pull up one of those.
The fitting error. So it generates the KFTP at several temperatures, several pressures, tries to fit them with the Chevy Chev. Usually it fits. Sometimes it doesn't fit, and I think it tells you that by the bed is it fit.
If you run Arcane independently, it definitely tells you.
Yeah, I think it does here. Right?
So this is a PS network file.
I think this is an input file.
Yeah.
Since it's an input file, you can
Yeah,
run
you
it
can run it
independently,
on-
and then Arcane will tell you the
Arcane.
speed.
Yeah. How about in the RMG input? Did it just have it? That was there. Okay, we have this warning. Actual expected KF. Yeah. So okay. So these things.
So
I
that's not
think
French
these
fitting.
warnings are telling you that the fit is not fitting, I believe. We need to make clearer warning statement.
Yeah.
I think that's what they're saying, is that we expected these two numbers to be the same, and they're different. And I think this is a fitting error, but I'm not sure. And this one definitely is error of the equilibrium constant computed using discretized energies compared to the original value. They should be the same, but you can see they're off by 50% or something. You'll get this is pretty common. This one, I don't know how close it should be, but this seems pretty bad, actually. So like factor 3.
I think the threshold that this checks for is like factor 2.
Factor 2.
Within factor 2, it accepts it.
Okay. So I don't know what you can do. If it says it's bad, I don't know if you increase the number of Chevy Chev coefficients, will it get better? I don't know. It might be worth a try.
Yeah, I remember running into some nasty problems if you use, I think the common example used to have way too few Chevy Chev coefficients.
And then yeah.
If you run it, it would just break and get upset with you.
Yeah. So this kind of stuff, if you find one particular PDEP reaction you care about, it's very advisable to go to Arcane. And then you can play with that one individually and get all the parameters set so you really believe it. And then you'll know what you're doing. This is a pain to modify stuff inside RMG because you have to generate the whole RMG job every time you rerun.
Is there anything else you want to look at?
I wonder if it's easy to show how different the PDEP result is from the result you got before.
I mean, we could run this one.
You just rerun it with PDEP off. Again, you can see the results here. And then,
Well, what kind of results did you want to see?
like a plot of one species going away or something.
Okay. Is it the same simulation profile or same simulation profile? Plural, right? Yeah, this will take a couple of months. And the example takes about 2 minutes. Although that might be 2 minutes after it starts simulating. Or the RMG thing stuff actually starts. Hopefully in the future, once we have the compiled trees, we won't need to load them anymore. We won't have to send the training reactions, and that'll save a lot of time. So that's the PDEP one. And this is the not PDEP one, which, as you can notice, then it's a whole lot faster than PDEP one. Let's look at
all right, you said a really short termination time.
I think, yeah. Sure, this example is very. I'll just drop the. Should I just drop the tolerance to like.
Which one?
Or actually, I can run the simulate script on it. That'll be a good introduction for the script selection.
Sure.
Yeah.
Okay. So How long should I run this for? 100 seconds? 10 seconds? 10?
Maybe.
Okay.
I'm not sure.
Okay, Max has spoken. Okay. And let's put this. And then. Okay, so we're launching the simulate script here.
It's for the high pressure level.
Yes.
Windows.
This one's finished. So let's do or maybe. Oh wait, it's shorter time. It's really short time scale, not really long time scale. Try that. Maybe more. Sorry. For what? The director you're in, or?
Yeah.
Yeah. Yeah.
Oh, okay.
There we go.
Okay.
This one's PDAT. This one's not PDAT.
Do you see how much faster the be done once? It's like many words magnitude faster. Left.
Left is PDAT.
Yeah.
Right is high P limit.
So for these small molecules, there's some chemically activated steps that like skip over several welds. It's way faster than going down into the welds. So the kinetics are way faster. You see how it's like boom. Reacted. Yeah, I was thinking similarly, like Matt showed an example yesterday with the hydrogen oxygen. And in his case, the main reaction was H2O2 oxidizing. But in reality, the main reaction should be H plus O2 to OH plus O. But that's a chemically activated sequence. Just H plus O2 goes to HO2 star, goes to OH plus O. But that reaction is completely missing. So then the kinetics are way slower than they really should be.